check, check, check. Check and check, check to check. Okay, in this video, we are going to be looking at how we can design a finite state machine and use that finite state machine specifically to be put into code for an embedded system to run more efficiently. And the principal example that we're going to be looking at is using a line tracking robot. And this is all based on content from Chapter 7 of the book Introduction to Robotics Embedded Systems by Jonathan Valvano. The task is for our robot to try to follow a line and do so hopefully pretty smoothly. We've got inputs, which are sensors, and we've got outputs, which is controlling these DC motors so that the robot drives. And we are going to essentially encode the robot position or the way we're going to control the robot, and we're going to check the transitions based on what the sensors are telling us. Okay, so we're going to start with just a pretty simple robot that has 2 wheels and 2 sensors, and those sensors tell us whether the robot is on the line or off to the left or right when we're really developing a good tracker. If the robot does not see a line, one of the things we want to know is whether it's off to the left or off to the right. We've got 2 sensors which serve as our inputs, and those sensors are the left sensor and the right sensor. And we're going to say if I have 1, that would say that both the left, which is the first argument, and the right are on at the same time. And there's really the different possible inputs. Like if they're both on, the robot is on the line. If the one on the left is on, but the right one sees nothing, then that means that it's off to the right. And the opposite is true. If it's 0 for the left sensor, it can't see a line. If it's a 1 on the right sensor, it can see the line, so that means that we're off a little bit to the left. And if you can't see anything with either sensor, then you're not on the line at all. And then we can control the motors, and again, the motor control is done by setting things to be high or low. Turns out that in order to turn right, we can essentially set the left wheel to be on while the right wheel is off, and if I want to turn left, I turn the right wheel on while the left wheel is off. And really, again, determining whether it's off to the right or left is important, and how we actually do the control also matters. So just a graphical definition, right, where I'm either on the line, I'm off to the left, so the top one is on the line, next one's off to the left, off to the right, or in no man's land, either off to the left or right. What do you do? So in general, our strategy is going to be to churn by slowing down a wheel. So we want to slow down the wheel in the direction we want to turn. We want the other wheel to be faster. So we can do that really in all the different situations. And we want them to, both wheels, to go at the same speed if we're going straight forward. So that's roughly the strategy we're going to try to follow. And to do this, we're going to work through all the possible combinations of sensors and what we would need to do for the output. And we're going to construct a state transition graph. In this case, I'm using the notation that left means move left and right means move right, although we'll see a little bit later a different formation of that. So let's start with, if I'm already in the state center where I'm going center, straight ahead, and I still see the line, I can continue to go straight ahead. So that's the case where left and right sensors are 1, and I need to be in the center. If I'm off to the left, which means that left sees nothing, right sees a 1, I need to turn right. So I would transition out of center to the right. And if I am in the center currently and I'm now off to the right, meaning that the left sensor sees the line, the right sensor sees nothing, I need to turn to the left to get back to the line. Now we're going to work through, turns out that anytime that I am seeing both a left and right, I just want to go straight forward, and that works all the way around. So no matter which state I'm in, If both sensors are 1, then I want to go center and go straight ahead. If I am off to the left, I always am wanting to turn right. So this is sort of a very simple line tracking strategy. And that is true no matter which way I'm off to the left. If I'm already in the right state, I want to continue to go right until I get out of the off to the left state. Same thing applies in reverse. So if I'm in the left state and I am off to the right, so I'm commanding it to move left, I want to go to the left no matter what. Now, what we haven't talked about is what we do when we're lost, and so we're going to just sort of address all of those things right away. So it turns out that in this case, if I'm at center or left right now and I'm off in the middle of nowhere, I want to turn right. And if I am currently in right and I'm off in the middle of nowhere, I want to turn left because I've overshot where I wanted to go. And that's really the approach that we're going to take here. Now, the problem with this is that the tracker exhibits oscillatory behavior. Like, it's going to overshoot and then it's going to correct, and it might overcorrect and then it's going to overshoot, and we really don't want this to be how we do it. And part of that's because we're taking big steps. Like, so one simple option to improve the line tracker is to take smaller steps. So instead of going from the state left to the state right, if we go to the center first, that reduces the step size and makes it so it's a little bit better. Another way to do this is to use feedback control, specifically something like PID control. That's not something that I'm going to talk about in this video, but it may be something I address a little bit later. So essentially what I'm saying is if I'm currently in the left state where I was previously going all the way to the right, and if I was in the right state and going all the way to the left, I am going to change that so it goes to the center first. So those are the big changes to the state transition graph. You can see it in blue. And so when I do that, I get smaller steps. It may still oscillate, but those oscillations are going to be smaller and we aren't going to overshoot quite so hard. Of course, there are better ways to do this, actually using feedback control, but this is a step in the right direction. So the textbook that this example comes from, they define the states differently. Instead of using left to be turn left, it's left to make the left motor high. In other words, turning right, and the right state is having the right motor high or going left. That's very confusing, but if you really look at it carefully, you can actually say that the state table, which is laid out essentially a tabular form of that state transition graph, that state table is identical to what we have already developed on the previous slides. So take some time thinking about that. The output is just based on how we're going to connect. So essentially, if the output is 1, I'm going to be, and that's a hexadecimal value of 1, I'm going to be commanding the right motor. If it's 2, I'm going to be commanding the left motor, and if it's 3, I'm commanding both at the same time, so both would be on. Again, because in hexadecimal, 1 would be the first bit in binary, 2 would be the second bit in binary, and 3 would be both bits together. So we're going to see actually the code that implements this table on the next couple slides. So in this code, we're creating a linked data structure using the struct key term. And we've really got 3 inputs. I've got an output, which is an unsigned 32-bit integer. I've got a delay, also an unsigned 32-bit integer. And then I've got a constant, which is another structure, again, state, but we're really pointing to the next 4 items, and we'll cover that. Essentially, we want to do next if the next 2-bit integer is from 0 to 3. We don't want to do it if it's something different. So let's then define the state as state t. And what we're going to do is define center, left, and right. And those are just different locations in my finite state machine. State t is FSM, finite state machine, and it's got these three rows. And those rows are essentially the same. Let's go back up. It's the same as the state table here. So in other words, center would be 3. That's with both on. So let's look up there. You'll see both are on. We're going to set the delay to be 500 milliseconds or half a second. And you can see the different states that go along with this. And it totally depends on what the sensors are doing. And then we'll do the same thing for left. Remember, left is commanding the left wheel or turning right. Then we'll do the same thing for right, which commands the right wheel or turns left. Then we'll create a pointer to the current state. And then we define the input and the output, which is where we're going to get our sensor inputs. And then the comments kind of define these things here. So that's all the setup. The next thing to do is to implement our main function. We're using clock init 48 millihertz, so that way we can do some timing. More time stuff will happen later. We do the other initialization, and we're going to set our initial state to be center. So go forward, and then we're going to do some stuff. Set the output from the finite state machine. We're going to make the output actually work on the motors. Then we're going to delay and wait as long as we need to delay. It's a clock delay of 1 millisecond, so if I have 500, it's going to be 500 milliseconds. Then we're going to check the input. So essentially, we're going to go forward for half a second, then we're going to check, and then we're going to make a decision. And then we just specify what the next state will be, and we continue to do this until we run out of lines. Here's how you would hook this up. Although in the launch pad that we're working with, all of this hardware is implemented already. So you can see how I've got 2 different transistors that are going to run each of those motors. And then you can see what we're using. We've got pins for the motors and pins for the inputs. Those things are already there. That's what we're going to use. And if you would implement that code, if you're using the robot that's covered in the book, you should be able to get your robot to more or less follow a line. And there's always ways that this can be improved, but this is a simple way of walking through what we would want to do with a robot in order to get it to follow some lines. You should definitely work some problems where you have to develop all the logical states and then put that into code, but this should at least get you started. That's all. Thanks for watching, and I hope you enjoyed the video.